Hello, class. We are continuing with Geographic Basics, Introduction to the Earth, and this is the second half of the lecture. So we will begin with looking at the physical Earth, and the physical Earth is not actually a complete round sphere. It's what they call an oblate spheroid, meaning it's not quite round and it has a kind of a bulge at the middle of the Earth, at the equator or in the tropics. And this is called the equatorial bulge, and then you have polar oblateness, meaning from pole to pole, this is shorter in diameter than across the equator. This was first learned back at the time of Aristotle and Eratosthenes, and they were able to compute using angles, so geometry. They went to two locations in Greece or in Egypt, I'm sorry, and took angles to the sun. And through this, they actually measured this distance. They came within 2 miles one direction and 24 miles in the other direction, which is incredible, thinking that they could even compute this. So they understood a lot about the Earth. We tend to think that everyone thought the Earth was flat in ancient times, but that was not the case with the navigators and so forth. They understood the Earth was round. This knowledge was suppressed heavily by the church. So lay people were taught that the Earth is flat. But these early scholars proved to us that they understood clearly that the shape of the Earth and um, just factors of its location, even in the universe or in our solar system, related to the sun and so forth. However, these early scholars didn't understand why the Earth would be thicker in the middle than from pole to pole. It wasn't until Isaac Newton came along centuries later and he learned about the force of gravity and then the centrifugal force. So the Earth is in its constant spin like this, and then the Earth is not just a solid rock. It's got all these layers, concentric layers that compose it from the solid iron core that have different textures, and um, some are flexible, some uh, are brittle, such as the outer core that we stand on, and so forth. But because there is flexibility inside, and when you have the Earth spinning, it's like being on a merry-go-round. So at the axis, the North and South Pole, which is where the spin occurs, so the Earth's going around on the spin with this axis, this would be like standing at the center of the merry-go-round if you're standing at the North or South Pole. And if you were standing there, you're moving 0 miles per hour in this rotational spin. If you're standing here at the equator, you're going over 1,000 miles an hour. And that is what causes everything inside the Earth to shift and push outward, because it's like you're being pushed, like just like a merry-go-round. When it's going around, you're being pushed out on the outer side of, you're standing out on the edge where it's fun, right? That's where the action is, and it's pushed out. And this also has that effect of making this center part of the Earth pushed out a bit. The equatorial bulge, polar oblateness, going from pole to pole. When we look at the Earth, we also know that the surface of the Earth, that is our home, what we call the lithosphere, or our landscape, it is not smooth. It's got multivariance to it. And it's showing here in this diagram, the deepest point is the Mariana Trench, going over 36,000 feet deep. And then Mount Everest, which is over 29,000 feet high. So this is the highest point on Earth, the deepest point on Earth. And so we have the spectrum of everything between this. And of course, we see this on the continents where it's not submerged underwater, but even under our oceans. Uh, this has a multivariate landscape. It's got the deep trenches, the mountain ridges, the plateaus. It replicates much of what we see on our active surface landscape. Let's look at how the Earth is divided. So we have the grid system, and the grid system is based up on the orientation of the North and South Pole. So our Earth's axis, that's the spin of our Earth that um, creates this axis. And we have what we call the plane of the equator, just like I mentioned the plane of the ecliptic, which is the the pull of the sun's gravity, keeping all the planets in a rotational field around it. Well, the Earth is also spinning, creating its rotational field of gravity, which is called the plane of the equator. So let's look at the geographic grid. The geographic grid creates what they call absolute location. It was created by these early scholars, Aristosophanes, who's called the father of geography, Aristotle, all these great scholars, and these are just the top names of people, but there are many people below them that also compose this geographic grid and all the theory behind it. At any rate, this is what is called absolute location, and we will talk in contrast to absolute location, we will talk about relative location in lecture 2. So we will go back to this term then. But absolute location is basically a mathematical location that they've designated that they can designate for every single place on Earth using the latitude and longitude, or the geographic grid. So we said that the Earth's rotational axis acts as the basis of division. So this is how they start the division. So we've got this, and they cut it in half. Here's the equator, and that's how we start. We start with latitude. Latitude lines, or if you're referring to the whole latitude line, that is called a parallel, this term. Latitude lines, or parallels, they are divided from the equator. So they've used the axis of the North and South Pole, and they've cut the Earth in half. They're using geometry here. And then they've simply laid, basically, going back to your geometry class, they've laid a protractor down, and then they've measured up 0 to 90 degrees and marked them off. Every degree's off. So it's going in equal distance between each degree. Equal distance. So this is different from longitude lines, which are not equal distance apart, but latitude are. However, only one latitude, the equator, encircles the entire circumference of the Earth. All the rest of the latitude lines go to increasingly shorter lengths until you get to the North Pole, and it is simply a point on the Earth. So they're equal distance apart, but they are not equal lengths around the Earth. And that becomes important when we start to compare them to longitude lines. There are 7 important latitude lines, and we'll look at them in the next slide. And there are also what they call latitudinal zonations that indicate a kind of a temperature bands, or climate zones on the Earth. Here are the important parallels. So the equator, which is right here, and you go 23.5 degrees north and 23.5 degrees south. Here, it's the Tropic of Cancer in the northern hemisphere. 23.5 degrees south is the Tropic of Capricorn in the southern hemisphere. At 66.5 degrees north and south, you have the Arctic Circle, which is up here for the Arctic Circle, the northern hemisphere. and Antarctic Circle down here in the southern hemisphere. Then the final two important latitudes are 90 degrees north and 90 degrees south, North Pole and the South Pole. So remember, the Arctic Circle is different from the North Pole. So Santa is at the North Pole. He's not here at the Arctic Circle. These are very different. This is 66.5 degrees, not 90. So many people make that mistake. I'm sorry. All right. So back to this. All right. So you need to remember all these. So memorize these, memorize their degrees. You will have that on your exam. All right. One important thing that we'll be talking about throughout the semester are the latitudes and what climates come with them. Of course, you guys know that down at the equator or the tropical latitudes or tropical regions, it's very hot. And this is where the sun is always shining directly overhead all year long. The sun's direct rays basically move from directly overhead at 90 degrees between the Tropic of Capricorn and Cancer. We'll be talking about that, and I'll be describing how that occurs as we go throughout the next this chapter and the next few chapters. So, or lectures. And we know at the equator or the tropics, it's very warm, and down at the equator, it's very humid. Okay, these are the most diverse ecosystems in the world, or biomes, and that's because every day down at the equator it is raining. Every day it has direct sunlight coming in. Every day of the year. The temperatures range only about 3 degrees, so the average is about 88 degrees, and it only varies about 3 degrees, either above or below 88, every day of the year. This area of the world is called the seasonless latitudes. The sun comes up at 6 a.m., the sun sets at 6 p.m. every day. They don't have the very distinct seasons that you will experience if you live up in the mid-latitudes here or down here. Of course, down here, the southern hemisphere is called the water hemisphere because there's not much land mass, and the northern hemisphere has most of the land. So when we refer to the mid-latitudes where all the people are, it's basically up here in the northern hemisphere. Okay, so this is the seasonless latitudes, and then notably, this is where all the biggest rainforests are. So here's the Amazon Basin, the largest rainforest in the world. Here's the Congo River Basin, the second largest rainforest here. And then over here in all these islands through the Philippines, Indonesia, and so forth, these are the third area of heavy rainforest cover. And as I mentioned, this is the most diverse part of the world. Then we go to the subtropics, 23.5 degrees north, so here at the Tropic of Cancer and Capricorn, to about 35 degrees north and south. This is where you find the world's biggest deserts. So here is the Sahara, the largest expanse of desert land. Here's the Saudi Peninsula or the Arabian Peninsula. With the roof of the world, the Tibetan Plateau. And this is a high, cold, dry desert also. Over here you have the Sonoran. And then down here you have the Namib and the Kalahari. Out here is the great outback, the extensive expanse of desert. Over here is the Gran Chaco. So the subtropics are noted for the desert regions, dry and sunny, little rainfall. Then you go to the mid-latitudes, 35 to 55 degrees north. The mid-latitudes are the notable winter, spring, summer, fall. Winter, spring, summer, fall, the 4 seasons annual pattern that we would go through and experience. you'll notice that Los Angeles, um, we sit right at the edge of that. We're at 34 degrees north latitude, and we do have kind of a semi-arid pattern. We're quite hot and dry, but yet we do experience a soft change of seasons every year. And that's because we're over here right on the edge of that. You'll notice that Italy and all of the Mediterranean here is also on that same latitude. And if you look at pictures of Italy and Spain, it looks just like you're in California. They are also in what they call this is called a Mediterranean climate, this area. And it's only on the west coast of the continents. Here in the Mediterranean, it goes clear around it. Okay, so let's look, and then we go to the subarctic and Antarctic. This is where you have the deep tundra and so forth. And then up here above the Arctic Pole and the Antarctic Pole, I'm sorry, Arctic Circle and Antarctic Circle, up toward the North and South Pole, you have the deep, deep freeze with the heavy, heavy perpetual ice sheets. Let's look at longitude. So longitude lines, they are all equidistant from the North Pole to the South Pole. They run around the entire Earth, 360 degrees, and now they have to cut the Earth in half because this is how we're going to make time by using, because this is the Earth's spin, and the Earth spins through the daylight hours when it's facing the sun, and then it falls into the shadow of the sun at night. We go through our nighttime hours. So the spin of the Earth toward the sun and toward the shadow of the sun is what we call a day. Therefore, if that's what we are denoting time with. So we said that one pattern of light and darkness equals 1 day, we said. And then our one revolution around the sun through the seasons, that's 1 year. And then we have the moon, which is going around the Earth, and its revolution, we say about 1 month. That's how we get our designations of time. The one time that does not work is a week. That is a human fabrication. It has nothing to do with the light and the sun and earth relations or anything in our planetary fields like the moon or anything. So longitude is important because now when we cut the earth in half, it's going to designate where we start to count a new day. And in this case, we don't have the axis, the North and South Pole, to cut it, to designate the Eastern Hemisphere and Western Hemisphere. So this was a decision made by scholars. And it changed about through time. Today, they identify 0 degrees longitude as running through Greenwich, England. And then the opposite side of the world over here is the international dateline. So this is the prime meridian, international dateline. The term meridian is just like we said for latitude. If you want to refer to the whole line of latitude, it's a parallel. And for longitude, if you would like to refer to one line of longitude, you can refer, it's what they would call a meridian because you're referring to the whole line of it. So this is the prime meridian where we start to count, and then they just took their protractor again, laid it down, and measured off half of the world, 0 to 180 in this case, east. So that's the Eastern Hemisphere. 0 to 190 west is the Western Hemisphere. So whenever we cross the date line over here, that's when we designate a new day. Let me just go back. I forgot to mention one thing. Longitude lines are very different than latitude lines because we said that longitude lines remain equidistant between the whole line, between each parallel. Meridians don't. They are widest apart at the equator, and they get progressively closer until they converge at the poles. That creates, because this Earth is a circle, so now when we want to create maps, it's going to be a problem because when we try to flatten out the Earth, we've got these converging lines. So every map is going to have distortion because to lay this information down flat, it's going to be like taking an orange peel and trying to flatten it out. You'll have to either stretch it or tear it. And of course, we'll talk about that in the next lecture and Introduction to Mapping. Each line is the same length though. Remember that latitude lines, each one gets progressively shorter as it goes toward the poles. Okay, now let's look at seasons. So there's three important conditions. What they call the declination of the sun, or what they're referring to is the subsolar point, which means where is the sun shining directly overhead on the earth, so at a 90 degrees. What latitude is it hitting? Because our earth sits at a tilt to the sun, which we'll talk about as we advance through this topic. And therefore, as we go through that revolution around the sun, then the latitude that the sun is shining directly over, it moves. Well, that doesn't move, but the sun's rays move on the earth. So the subsolar point is where is the sun shining directly overhead? Then the solar altitude is the angle at which the sun is shining above the horizon. If you notice in the winter, it appears as if the sun is coming up in the morning or setting as if it's way down in the southern horizon. And then when summer comes, like right now, it seems as if the sun is shining directly overhead. It's not shining directly overhead here in Los Angeles, but it does appear to be. So that is what they're referring to. What is that angle? Solar altitude. Where is it in our sky? So that will vary according to the time of the year it is. Then we have the length of day, which relates to how we look at the circle of illumination of the sun shining on the earth. So in the spring, our daytime is getting longer. In the fall, our daytime is getting shorter. So our shortest day of the year in the north, and I'm speaking about the northern hemisphere, is at winter, at right before Christmas. And then our longest day, when we have the most sun from the earliest time hours of the morning to the latest hours of the evening, is in the summer. So that's what they're referring to when we talk about the length of day related to the circle of illumination. So we'll go through these processes and you will start to see what each of those means. First, let's look at the revolution of the Earth around the sun. So our Earth takes about 365 and a quarter days to completely rotate around the sun. We rotate on what we call the plane of the ecliptic, and that's the gravitational pull of the sun. And then we said there's the aphelion and the perihelion, where the Earth comes in a little bit close in the winter, again speaking from the northern hemisphere perspective, and then swinging out a bit in the summer, the aphelion. So it doesn't revolve in an even pattern. And I put down two bits of information. You don't have to remember these. You definitely need to remember the aphelion and the perihelion. But I put 93 million miles is the average distance the Earth is from the sun, and our miles per hour that we are traveling around the sun is about 66,660 miles per hour. Again, that I just put that down for trivia, fun facts. You don't have to remember it. Then we have our Earth's own rotation, which we go into a complete rotation once every 24 hours, which we call a day. I mentioned already that the Earth is like a merry-go-round. So here's the axis, and then this spinning around. So if you were standing up here at the pole on a merry-go-round, let's pretend it's a merry-go-round. So you're on the Earth merry-go-round, and you're standing at the North Pole. You stood still as the merry-go-round went around. You would move in a circle, like you would face in a complete circle, but you would be at 0 miles per hour. You wouldn't you wouldn't be moving in distance. You would just be turning. And then if you're at 40 degrees latitude, so I mentioned that Los Angeles is at about 34 degrees latitude. So if you're at 40, it says you're going around 800 miles per hour. And we are a bit south of that. So we're toward the equator. And the equator is spinning a little over 1,000 miles per hour. So in Los Angeles, we're spinning a bit over 800 miles per hour. So this is um, this again is not something you guys need to remember. This is just like just interesting, I thought, and I thought it would help you understand how the Earth is operating, just like a merry-go-round, and hopefully you can remember some of these dynamics. If you guys were going to be a pilot or something, you'd definitely be having to learn all the equations and calculations that would go out for this, along with all the movement that you would have to do for your airplane and so forth. But for this class, I just put it up there for interest and explanation. You don't have to remember that part. Let's look at the rotational effects that happen on Earth. So here the Earth is going around the sun. It's also passing by all the many, many planets and things, or stars and so forth, that are also up in the up in space. And then our Earth is also spinning itself. So this has what they call rotational effects. And the first thing that's important to look at is the Coriolis effect. So the Earth is spinning, and then all of the bodies that, the heavenly bodies that are out here around it are going to exert some pull on the Earth. So for instance, we know that the moon pulls the tides of the oceans in and out. So I said once a day. Tide goes in, the tide goes out, comes in. And all of the oceans actually respond from the pull of the sun. So as we're going around in this spin, it creates a clockwise pattern for all the oceans to spin in the northern hemisphere, and a counterclockwise spin in the southern hemisphere. It also has a pull on our atmosphere, and that air follows that same pattern of the oceans, clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. We will be talking more and more about that. Then we have all of the influences, because we ourselves are composed of 70% water. So we've got all of the things that happen to our body because we were evolving here on Earth, right? We evolved here on Earth through all the multitude of time and steps, and basically we began to evolve. We're a product from the beginning of the Earth. We're actually even deeper than that because we're all composed of stardust. But essentially, just looking at our body and the outcome of it, it has all of these effects also built into us. Those are called diurnal alteration or circadian rhythm effects. Diurnal alternation means that you're going from light to dark, and then the circadian rhythms are the outcome out of that, the influence, the patterns that emerge. So when we look at plants, different animals, our human body, each one has its own unique characteristics. Sometimes many of them correlate, sometimes they don't. So let's just look and think about humans, and then just think of going camping, if you guys have been camping. And you might think, I'm going to sleep in tomorrow. I don't have to do anything. I'm out here having fun. Even if you're in a tent, it's almost impossible to sleep in once the sun comes up. That's because you are part of this diurnal alternation since the eons of time. And our bodies, we're a daytime animal. Our eyes pick up that visible light. We've evolved to do that. The minute the light begins to emerge from the sunset that's coming, our bodies begin to react if we're out in nature, not if we're in a darkened room in our house with heavy curtains or something, but if we're out in the light, and our bodies start to react. And we can't block out the sun just by closing our eyes. The light will still come through our eyelids, and it sets our body into motion. Your digestive tract starts to pick up. Everything, it basically starts to wake you up. The same reverse happens when the sun starts to go down. Late in the afternoon, when the sun is going down, if we don't have electric lights and things to turn on, your body will, if your heartbeat, everything starts to slow down, and you will go into like a kind of a hibernation. So if you didn't have any light available, there would be nothing that we could do in the night if we didn't have electricity and candle lights and things. We would have to just wait till the sun came up, right? And that's one of those responses to this pattern of light and darkness as the earth turns. Our body has so many, I can't even go into all the influences that have evolved from the circadian rhythms, but the way we eat, if we were naturally in this rhythm and weren't artificially influenced by our technology, um, is what we've evolved in. The waking up early, going to bed when the sun is setting, all of those patterns, the way your body digests food and so forth, it all has to do with circadian rhythms and our evolution of time through this, because it's only been a second that we've had electricity and candle lights and so forth. Um, the moon, I mentioned, it has the tides. The moon also influences our body, and we have many kind of patterns, like the way our hair grows and things, that our growth spurts, hair growing, hair falling out, things related to moon patterns and the circadian rhythms. These are natural patterns that are, it's not just from being sick or something. Okay, so let's go on. Then we have the tilt of the Earth's axis. So showing you, here's the plane of the ecliptic. That's where the sun is shining at its intersection, pulling the Earth in its gravitational field. And then here's the plane of the equator. Here's the North and South Pole, the axis, and that's our spin. That's called the plane of the equator, we said. Over here in this diagram, they're trying to show you the crosshairs of the plane of the ecliptic here and the plane of the equator. Now, you'll notice that this is going to correlate with the 23.5 degrees for Tropic of Cancer and Capricorn, and the 66.5 degrees that correlates with the Arctic and Antarctic Circle. And so you'll be like, oh, okay, that's where they're getting those numbers. And of course, that has a correlation to where the sun's direct rays are hitting the Earth, the subsolar points. So here, they're measuring this angle between the plane of the equator and the plane of the ecliptic, 23.5 degrees. If we draw a line here, now we get the Tropic of Capricorn. And then opposite angles are equal, we learned in geometry. And 23.5 degrees north gives us the Tropic of Cancer. Then you'll see here, this is 66.5 degrees, all right? So it correlates here. Let's do it on this side because we want to draw the Antarctic Circle and the Arctic Circle here. But all these angles are 66.5 degrees, right? So now if we draw a line here, we get the Antarctic Circle. And if we draw a line here, we get the Arctic Circle. So just as an introduction to those important parallels, you can see easily how this has started. Let's continue. Looking at the axis of the Earth, we have axial parallelism, which means that the Earth, as it's rotating around the sun or revolving around the sun, it remains on its rotational axis. It's in a steady state equilibrium. Here's the North Pole, pointing to the North Star. It's staying firm in its axis. And it's going around the sun, remaining on that axis. It's not wobbling around, no, it's staying in this orientation. Therefore, as it's going around, because this axis is 23.5 degrees different from the plane of the ecliptic, then you will see the sunlight is changing its orientation on the Earth. So another important point about this axial parallelism is that if the Earth did not remain in this steady state pattern with its axis pointing to the North Pole and going around the sun constantly, ever present, we would not be able to have the evolution that we've had on Earth. Because for anything to evolve, you must have constant repetition. And this is for anything at all, even for us to go to the gym. Say we decide we're going to get in better shape and we decide to go to the gym. They say you must go consistently for at least 21 days to get that pattern started. And then once that starts, you can start to have your muscles will start to respond and they will start to speak to you and say, are we going to the gym today? Let's hurry up, because you've got them into a pattern. So because the Earth has been in this steady state equilibrium of revolution around the sun with this 23.5 degree axis to the plane of the ecliptic, we have evolved those very characteristic patterns of seasons. The Earth is also round. It's not like a cube or something. So when the sun's rays are shining down on the Earth, you've got light that it hits the tropics and the equator. It's overhead all the time there, so it hits it directly. But then the light wraps around the remaining latitudes. Right? So these are oblique angles, not direct, like at the equator. If you had the shape of like a cube, then it would be square here, and that would all just be direct. But because it's round, you've got this kind of wraparound of light, and therefore it creates a pattern where it's showing here at the equator, you're getting the direct light. If you were to shine a light bulb on the Earth right here, or a flashlight on the Earth right here, then it would just be the heavy light would just be a small area. So it's shining like right here. If you just shined it down, it'd just be this much. Then that light over here, though, that's wrapping around, it will spread over a larger area, but it's less strong. And finally, at the poles, it's going to be over a much larger area, more diffuse lighting, and much weaker lighting. The light also has to pass through a deeper and deeper amount of pathway through the atmosphere. So that also contributes to, like the poles, constantly in a deficit of light compared to the tropics. So if you thought of going out in the midday sun and looking up at the sun, and you would see kind of a bright whitish light that would be too brilliant to even look at. And then in the sunset time, you would be looking at light that's going through lots of pathway of the deep atmosphere. So you're looking across the whole horizon. And that's basically what happens as this light wraps around the earth as well. So we have an uneven distribution of sunlight. So we said the subsolar point is the only point on earth that's receiving insolation or sunlight perpendicular or directly overhead at a 90 degrees angle to the surface. That's what a subsolar point is. And we will be looking at where is the subsolar point on different days of the year, because that's going to tell us like the dates of the solstice or the dates of the equinoxes, and then the important implications of that as it's related to our seasonal patterns. The tropics always receive more concentrated sunlight because of the Earth's curvature, and they receive 2.5 times more than the poles. So the tropics are always in a surplus of energy, and the poles are always in a deficit. That difference is what triggers all the different systems that have emerged on Earth. Because whenever you have a system where there's an imbalance, so the Earth has more sunlight at the poles, more sunlight at the tropics than at the poles, then because the Earth is acting as one system, it's going to try to blend or equalize. And that gives birth to all the different systems we'll be looking at. Let's look at 4 special days. And you guys should memorize these. So we've got 2 solstices and 2 equinox. So let's look at the equinox first. And then you'll notice I put down a line of latitude, a parallel underneath each one. That's where the subsolar point is on this particular date of each year. So the equinox, so you should memorize these. The spring equinox on March 20th or 21st, the sun will be shining on both of the spring and fall equinox. The sun will be shining directly over the equator. And you can't really get this wrong on a question because it's telling you equal light, so the root word equal, and equal division, equal equator, which means equal division. So equal is here again. On the spring and the fall equinox, the sun is shining directly over the equator. Everywhere in the world is experiencing the same day length pattern. The sun is coming up at 6 a.m. and the sun is setting at 6 p.m. So it's twice a year, the whole world experiences the same day length, only on the 2 equinox dates. The solstices are completely different. So for the winter solstice, and I'll just speak about the northern hemisphere first. So in the winter solstice, and we called it the winter solstice because we're in the northern hemisphere, so December is our winter. If you were in the southern hemisphere, you would be in your summer. But on our winter solstice, the sun is shining directly over the Tropic of Capricorn at 23.5 degrees south latitude. That means that the southern hemisphere is getting more direct rays of sun than the northern hemisphere. So the southern hemisphere is in their summer, and the northern hemisphere is in our winter. That is our shortest day of the year. Okay, let's go. Then we go through the spring equinox, then we go to the summer solstice, and now the southern hemisphere is in their winter, and the northern hemisphere is now in its summer. So we call it the summer solstice. This is our longest day of the year. Sun comes up early, the sun sets very late. On this day of the year, the sun is shining over the Tropic of Cancer at 90 degrees. That's the subsolar point. The very next day after the summer solstice in the northern hemisphere, the next day will be a bit shorter. And then every day will get shorter and shorter until we get back to the winter solstice when we get to our shortest day. And then the next day will be a bit longer. And then we'll be going back. The days will be getting longer and longer until we get back to the summer solstice. Well, this is that annual pattern that we go in, and the southern hemisphere experiences the exact opposite. So you just need to remember these subsolar points, and on these days, this is where the sun is shining directly overhead. Like I said, the equinox days are easy to remember. The solstice days are a bit more of a challenge. If you like astrology, you can remember it through that because December 21st or 22nd is the cusp of going from Sagittarius to Capricorn. And of course, our ancient humans, they watched the sky. They knew all the constellations that were showing in the sky as we went through our annual rotation around the sun. And they named these times for those constellations. So here, the Tropic of Capricorn is showing in the sky. And then the summer solstice, you're going from June 20 or 21st, which is you're leaving Gemini and you're going into the sign of Cancer. So if you're an astrology buff, and you can perhaps remember it that way. I put up several different slides so you can see this kind of march of the Earth around the sun in our annual revolution. And so this one, it's showing the circle of illumination. It's showing, so here's the summer solstice. The sun is shining. So here we are on our axis, the plane of the equator, but we're spinning on the plane of the ecliptic. And the sunlight is bisecting the Earth like this. On the summer solstice, the entire Arctic Circle to the North Pole is bathed in light for 24 hours. As the Earth spins here, this top, because it's pointing off to the edge, it will never fall behind the shadow of the sun. So they will experience 24 hours of light. The Arctic Circle will be on our summer solstice. They will be in their winter and they will experience 24 hours of complete darkness. And then we get to the equinox here, and it bisects the Earth in half from pole to pole. So then we said the whole Earth, no matter what latitude you're at, will experience a 12-hour day of light, 6 a.m. to 6 p.m., and a 12-hour period of darkness. So the whole world experiences that same day pattern on the equinox dates. Then we keep revolving around the sun, and our Earth is now pointing, the northern hemisphere is now pointing away from the sun. We are in our winter. Here's the circle of illumination, and it's bisecting the Earth at the Arctic and Antarctic circles again. And now the Arctic circle is pointing away, so it will experience 24 hours of darkness, and the Antarctic circle will experience 24 hours of light. I put several slides here for you can take a look at them, just to orient yourself. This one's very descriptive about the North and South Pole. So of course we're looking at the North Pole in this, but it's the same in the South Pole, just reversed. But at any rate, it's showing if you're living from the Arctic Circle to the poles, then you're basically going to either be in like 5.5 months of light here. So the days will be very long, or you'll be, look at how dark it is already, the circle of illumination, right? Or about 6.5 months of darkness. It's a very rough life to live in these polar regions. If you think of all the countries, like Scandinavian countries or Russia, uh, me being from Montana, um, like same kind of pattern, not as extreme as the North and South Pole, but still the heavy darkness because you're up at almost 50 degrees latitude. And all these cultures experience like high alcohol intake and stuff because it gets very depressing. You're kind of in lockdown. You're just in your house, you're just hurrying outside to do things because it's very cold. And then the daylight hours are very short. Therefore, you're just mostly you're confined inside, and it's stressful, and domestic violence rates go up, and the drinking, high alcohol use, all of that goes on. You guys can watch Alaska Stormtroopers, and you'll see they're just going crazy. They go crazy in the summer if the people are out because they're going crazy because they're free and outside, and in the winter they're going crazy inside. But not a peaceful way to go through the seasons. So you can look through those. This is the day length chart, and then we've already been talking about it, but let's just look. So here's the winter solstice, and then the fall, the spring equinox, summer solstice, and fall equinox. Okay, and then here's the latitudes, 0 to 90. So we don't have to look at the equinox dates for the latitudes because they're all going, every latitude on Earth is going to experience the same day pattern, 6 a.m. to 6 p.m., 12 hours of light per day. So everything's the same. So we don't need to look at that chart. And we don't need to look here at the equator because every day is the same at the equator, the seasonless latitudes down at the low latitudes. So let's go to 30 degrees. LA is right here between 30 and 40. Let's just look. Okay, the winter months. Okay, so the winter solstice right before Christmas, it said we're going to be getting about, we'd be between here, so we'd be getting about 9.5 hours of daylight. So it says the sun would be coming up, you know, around 7:15 or so, and then it'd be setting between this 4:30 to 5, so 4:45 or so. And then we're not on daylight savings time there, so this sounds about right. Then you go to the summer solstice. Now we'd be on daylight savings time, so we'd need to add an hour. And then we would say that, okay, in Los Angeles, we instead of 14 hour, so we'd be experiencing about 14.5 hour day lengths, and the sun would be coming up about 6, and it would be setting about 8. So then if we go down here to 50 degrees, we'll look at the winter solstice. So Montana is about 48 degrees north, or where I was born at the Canadian-US border. And then says you're going to be experiencing about, or even less than 8 hours of a day length. So you're just going to be running to and from things, but you're going to be waking up in the dark. I was waking up in the dark going to school. I was getting home in the dark after school, and you're just basically running from building to building. It's just dark and cold. And then over here in the summer, though, now you're dealing with something beautiful because look, now your day length is 16 plus hours. And sun's coming up very early, and it says sunset's about 8 o'clock, but with daylight savings time, it's about 9. And then one thing that they can't show by, just putting up a sunrise and sunset, they can't describe what they call the twilight hours. So because of the low angle of the sun and reflectivity, the light actually lingers. So even though the sun is setting around 9, you would have light until about 10. And so you have these very long and beautiful twilight hours. It's really magical in the summer, quite painful over here in the winter. So if you don't ski or ice skate or something, where you really want to go out, it's pretty miserable. And most people, it goes beyond money barriers to do those activities. So they try to go do them. It helps your morale and your stability to be engaged in something fun. At the poles, then you go through winter solstice, no sunlight. The summer solstice, continuous sunlight. This is the Arctic Circle, and it's showing you in the summer, here's a sun angle. So the sun angle is never going to be high in the sky. It's never going to be up directly overhead, ever. It's always going to be very low. So what is melting the Antarctic ice shelf right now, or ice shelves, not just one, is not the sunlight that's streaming down. It's sunlight that's been absorbed in the oceans that's heated up the ocean water. They're being melted from below, not from above, because you just don't get enough direct rays of the sun to cause a huge meltdown. This is a time-lapse image. This is in Arctic Circle, and it's on the summer solstice. So it's showing this is the movement of the sun you would be watching across the sky. So here's the midnight sun, and it's going to go up a bit, but it's never going to rise high. This is the highest point. That's what they're trying to show here. So it's just going to move around the sky like that, but will never be high overhead, and it will never set on that summer solstice day. Here is solar altitude. Now it's showing that this person is standing at about our latitude, around 35 degrees. And it's showing here is the winter solstice, the equinox, and the summer solstice. So here it's showing the sunrise coming and moving across our sky very low at around a 26-degree angle in relationship to her. So here's the angle. Now, and they take it at the noonday sun. That's the solar altitude, the noonday sun. This is 50 degrees on the equinox dates. So again, the sun is still, low in the sky. It's not directly overhead. And then even on the summer solstice, even for us here in Los Angeles, our sun angle is still only going to be around 73 degrees angle. It's not direct. The sun is not directly overhead on the summer solstice. It does appear to us to be directly overhead, and that is because of the radiance and brilliance of the sun. So to the naked eye, we can't distinguish the actual sun, but it is not at a 90-degree angle to us. Any latitude above 23.5 degrees north or 23.5 degrees south, any latitude beyond that is the sun will always be in the northern hemisphere. For us, being above 23.5 degrees north, the sun is always in our southern sky. If we were in the southern hemisphere, below 23.5 degrees south, then the sun would always be in our northern sky. Again, like I said, if you're here in Los Angeles, though, in the summer, it definitely does seem as if it's directly overhead. Here's the analemma, and this little chart, if you take the lab, you'll find that you can find the subsolar point of the sun any day of the year. So if you looked here, it's showing you, so August 20th, and you have to make sure you're going the correct direction here. So you'd be going like August 20th because you're moving to September. And it shows, okay, the subsolar point of the sun is 12 degrees, and here's 0 degrees. Here's the latitude lines. So 0 degrees is the equator. So this would be the northern hemisphere. So on August 20th, then it's going to be 12 degrees north. And here it's showing like for October, then it will be, so on we're moving this way. So on October 15th, it will be shining directly over 8 degrees south. So here's the Tropic of Cancer, here's the Tropic of Capricorn, and the sun's direct rays only move this 47 degrees latitude. So if you live above the Tropic of Cancer, then the sun is always in the southern sky. If you live below the Tropic of Capricorn, then the sun is always in your northern sky. So we've got the spread of the solar rays over large and small areas. I just kind of summed it up. The tropics are warmer, the poles are cooler. Large seasonal variations in temperatures happen in the mid latitudes. And then we have the spin of the Earth. We have the international dateline that creates a day change. So this side is Monday, this side is Sunday. The Earth is always spinning in an eastward pattern. So if you fly from LA to Hong Kong, you're going to fly into a new day. And when you return, you'll fall back into the previous day. That's a human construction. It is not a reality. In the universe, time doesn't exist. Einstein tried to tell us time doesn't, it's a theory, it's a fabrication. Only the now exists. Eckhart Tolle he wrote his book telling us that. So the measurements we looked at were these are just official terms. Tropical years is one which we looked at, going through all the patterns that we saw Earthwise. But especially we noticed the seasons, the lunar month, we have the new moon, and the day we go through the period of light and dark. To get our time zones, we went through 24 time zones, and then we just to get these in longitude, we just take 360 degrees of longitude, divide by 24 hours per day equals 15 degrees per hour. And this time is based on the prime meridian and the international dateline. Just kind of summing up some of what we talked about. So here's the time chart, the prime meridian, international dateline. All the time zones are shown up here. And then down here, it's just showing related to, here's the prime meridian. So if you were in Moscow in the green zone, and you want to know what time it is in London, it says you would just subtract 3 hours. So it's going to tell you 10 to 7. So this gives you, this number down here gives you the relationship of every time zone to the prime meridian. Up here, they all go the same, 5 a.m., 6 a.m., 7. Nothing changes here. Just a day changes here. And these numbers are just showing in relation, like I said, to the prime meridian. Each time zone is based on 15 degrees of longitude, we said, and they have what they call a central meridian. It goes down each one. So if you were technically trying to find the exact time within that time zone, you would base it off of the central meridian. And we do calculate this out in the lab. I'm not going to do it in this class, so I just presented the concept. And here are our time zones for the United States. So we have the 3 hours difference between LA and New York. That concludes our chapter, and just make sure you go back through everything. I hope you've taken some notes, and then to study for your exam, I also put up the PowerPoint slides so you can also access those and look at your note and go through it, or you can go back through the recorded lecture if you want, just to double check if you have all the information. Thank you.